All right, so 9.4 is called parametric equations, and I said it yesterday, but it's not difficult. It's just that it's brand new. You've never seen parametric equations, which is going to happen when we get to polar as well in 9.5 and 9.6. A parametric equation is a set of equations that express a set of quantities as explicit functions of a number of independent variables known as parameters. These equations will introduce a third variable, t, and it represents time. So we are used to third variables being x, y, and z, and in parametric it is x, y, and t for time.
Can you see me?
All right, so we are going to graph parametric graphs, and these are the differences between a regular rectangular graph that we are used to and a parametric graph. On the left is your parametric, and notice that it's a combination of two equations. One's an x equals and one's a y equals. They both have t in them. So we'll start by just literally plugging in points, plotting the points, okay? And then they can be compared to a rectangular graph, which is what we're used to. The difference is, notice there's no arrows. So a parametric graph has arrows, and it points towards the time increasing. So remember, t stands for time. As the time increases, the graph on the left, my graph swoops down and then comes back up just like the shape of a parabola, okay? But the arrows, sort of like a vector, the arrows point towards the last t, the highest t. They will always be continuous functions, which means that they don't start and stop. They are functions, which means they would pass the vertical line test. Which means these cannot be turned sideways, okay? That would fail the vertical line test. And the points are this should be plotted in the order of increasing values of t. The arrows indicate the direction or orientation of the curve. So if it says to graph it and make sure that you include the orientation, that's what it means. It needs the arrows. Again, it points from the smallest t to the largest t. The definition of a plane curve. So if f and g are continuous functions of t on interval I, then the set of ordered pairs f of t and g of t is a plane curve. The equations given by x equals and y equals are parametric equations, and t is the parameter. So this is just some vocab here, okay? The actual equations are called parametric equations. T is a variable, but it's called a parameter here, and remember it represents time. And the way we will plot these is by literally taking t and plugging it into the y equals, or the x equals, and then t and plugging it into the y equals, and then you get your coordinate points. So that looks like this. You'll create a t chart, but it's going to have an extra column. So we're going to have literally t in the first column of our t chart. And then we get x, and then we get y. So here's where we're going to plug in our values. Let's say we plug in 0, 1, and 2. We're going to plug them into whatever equation says x equals, and we'll get those values. We'll plug them into whatever equation says y equals, and we'll get those values. And then we will only plot the x and y's, so we ignore the t. The t is used to find the values, but we don't actually plot the t. The way we show the t is the arrows. For the direction of the t, at least. We don't show exact t. All right, so this is what it's going to start with. Sketch the curve given by the parametric equations. X equals t squared minus 4, and y equals t over 2. Given negative 2 is less than or equal to t, which is less than or equal to 3. So that gives me my values to plug in. Less than or equal to means I'm going to include negative 2. So I'm going to start where t is negative 2. I'm going to go negative 1. I'm going to go 0. I'm going to go 1. I'm going to go 2. I'm going to go 3. It won't always give you the coordinate points there. Like it won't always give you the range. So you can plot points. You can start negative 1, 0, 1 if it didn't give it to you. On your test, I will give you the range because I want everybody's graph to look about the same because it will make it easier for me to grade. So just pay attention to that. All right, so now I'm going to start with the x, okay? I'm going to take that t and I'm going to plug it into x. So x would equal negative 2 squared minus 4, which is 4 minus 4, or 0. X would equal negative 1 squared minus 4, which is 1 minus 4, which is negative 3. X would equal 0 squared minus 4, which is 0 minus 4, or negative 4. X would equal 1 squared minus 4, 1 minus 4, which is negative 3. X would equal 2 squared minus 4, 4 minus 4, which is 0. And X would equal 3 squared minus 4, 9 minus 4, which is 5. Then I do the Y. Y equals T over 2. So Y would equal negative 2 over 2, which is negative 1. Y would equal negative 1 over 2, which stays as negative 1/2. Y would equal 0 over 2, which is 0. Y would equal 1 over 2, which stays as positive 1/2. 2 over 2, which equals 1. And 3 over 2, which would be 1.5. You obviously can leave it as 3 over 2 on your T chart, but when you graph that, it's going to have to be a mixed number anyways. So now the last column is just the X and the Y. We ignore the T. And then we go to our graph and we plot all of these. 0, negative 1. Negative 3, negative 1/2. Negative 4, 0. Negative 3.5. 0 and 1. And 5 and 1.5. And then I connect my points. So I start at the first one I got, which is the down here, wrap it around and go to the end. And then I am almost done. The last thing I have to do is give the arrows in the orientation of the starting point, the starting T to the end. There is no rule on how many arrows you need to put or where you need to put them. You just need to pay attention to the direction that they go in. Yeah.
I thought you said we can't turn it on its side because then it's still together.
So great comment. That's when these are functions. So if those said f of, then you've got to worry about it. But for now, we're just dealing with x and y's.
Okay.
Good catch, though. Yep. Like they're not gonna. Questions on that one?
So, could you use this for the problem where you're throwing the ball?
So a lot of times that's kind of what it is. It does like a velocity. Yeah. All right. Now, if you have your graphing utility, go back. We good? Yeah. Okay. All right. So if you have a graphing utility, I'm going to show you how to type this in. Obviously, this is great for checking work, not to be used on an actual quiz or test. So the first thing is we are now in a completely different mode, okay? When you hit the mode on your calculator, on a graphing utility, it's obviously here, okay? It's different for some other ones. But on that fourth line, it says function PAR, POL, and SEQ. We are going from function to parametric. So you want to go to that fourth line and you want to change function to parametric. On the newer TI, it has a full word parametric there. You want to click it. What this is going to do is it's actually telling your calculator that the variable we're going to use now is t. So when you hit the button that says x, t, theta, and n, it's actually going to give you a t now. Okay, so it's actually switched the actual function of the calculator to a different mode. Now we want to graph it. So if I were to go to my y equals, it also should give you two equations for each set. So I have an x1t and a y1t because there's two equations here. So let's just graph the one that's on the screen, 5t, and then 10 minus 16t squared. Hit graph. And depending on your window, here, let me show you what mine looks like, is how you're going to get your graph. So when I first graphed it, my window went from like, it was like negative 2.5 to something, and then again the X minute, it was so small that I couldn't see my graph. Hey. Alright, so I did the -1 because that's the smallest one, and then the 3/2 is the biggest one, and then I just did the whole numbers in between. So -1, 0, 1, and 3/2. Plug those into the X, and you should have gotten 0, -4, 0, and 5. Plug them into the Y, and Y is T this time. So I literally just duplicate that column over. So the coordinate point should have been 0, -1, -4, 0, 0, 1, and then 5 and 3/2, or 5 and 1 1/2. So then when you graph it, it should look like this. This one looks pretty similar to last time. They're not always going to look the same, but just keep in mind that they could. And then don't forget your arrows. So the arrows are important because this is no longer just a parabola. This is a parametric function, or a parametric equation, which means it's turned on its side, but it has orientation.
How do you know which side it's going? Like, why don't you put the arrow? Is it like supposed to be the longest side?
It's not necessarily the longest, but it's it points towards the biggest T. So our smallest, ooh, come back. Hey. Our smallest T gave us this point here, and our biggest T gave us this point, so you want them pointing towards the biggest. Questions so far? So tomorrow we're going to talk about a way to like eliminate the T so that you could approximate this graph. We'll get a little bit further in tomorrow. But I'm going to stop here for today. Obviously if you're a sophomore, you could have jumped off and started to attend math. I should have said it a while ago, but that's the case. If you owe me a makeup and you want to work on it now, then get yourself ready to do so. Okay, so now we're going to figure out a different way of graphing, which is to eliminate the parameter. So many curves that are represented by sets of parametric equations have graphs that can also be represented by a rectangular equation, like your parabola that you're used to, with just the X and Y. So the way we do this is we're going to solve, you're going to get two equations, the same two equations you would have normally gotten. We're going to solve one of those equations for T and then plug it into the second equation to eliminate the T. So it's almost like doing a systems of equation, but you're not solving for an actual number, you're solving for the other variable. And then you're going to get one equation, which will be in rectangular form, and you'll graph it, whether it's a line or a parabola, something like that. But it's important to realize that this is a loose orientation, or you're going to lose the orientation of the graph. So you won't know which direction it's going in. These are approximations of the graphs. The way that we did it the first time is much more specific and much more accurate, okay? For the last thing, it says the domain on the functions may need to be restricted to graph accurately. So if you think about our domain restrictions on our original graphs, like our parent function, we go way back, like we can't square root a negative number. So if you see something like that, you might have to restrict it so that it works. All right, so they say graph by eliminating the parameter. And it gives you the same two equations that we had the first time. X equals T squared minus 4 and Y equals 1/2 T. So I'm going to look at these two equations and I'm going to try to figure out which one would be easier to solve for T. So it's a systems of equation. Normally it doesn't matter what variable you solve for, but this time it does because we want to get rid of the T. So we want to solve one of these equations for T. Which one's going to be easier? The Y. So if I take that Y equals 1/2 T, and I want to get T on the side by itself, what do I do?
Divide by 1/2.
Divide by 1/2 or multiply by 2, right? So it's going to cancel here, and I get that T equals 2Y. Now I'm going to take this, and I'm going to plug it in here in place of the T. So I get X equals 2Y squared minus 4. And I'd get X equals 4Y squared minus 4. What kind of graph is this? It's a parabola. Specifically, what kind of parabola? What happens when the Y is squared? Sideways, right? So if we want to get this into standard form, what we're used to with our conics, the squared always comes on the other side, or on the side by itself. So I can move this 4 to be with the x. X plus 4 would equal 4y squared. I cannot have anything in front of the y squared, so I would divide both sides by 4 or multiply by a fourth. Okay, same thing. Equals y squared. And then go a step further and say that 1/4 can't be attached to the x, so I take that out. And 1 divided by 1/4 is 4. So you could have kept it like this. It's the same thing, okay? We're also used to the y squared being on the left, so if you want to rearrange it, you can. So in standard form, this is what my graph would look like. So we already said that this is a sideways parabola. Does it point to the right or to the left? The right, because it's a positive 4p, right? I don't need you to go much further than a direction and a vertex. You don't need to find like the focus and the directrix for me on this one. You just want to know that your vertex would be the opposite of what follows x. So -4, opposite of what follows y, 0. -4, 0. And it's pointing to the right. Yep.
I'm confused when you did that to regard the x plus 4 over 4 and then equals 4y.
So this one, right? That step.
Yeah.
So if you want, you have to get it into standard form. You have to get rid of the 4. You can't have anything in front of the squared term. So dividing by 4 is the same thing as multiplying by a fourth. If you distribute that in, you end up having to take it back out anyways, because there can't be anything on front of the x. So you can actually just leave it as 1/4 x plus 4 equals y squared. And then I just flip-flopped it to the y squareds on the left like we're used to. So now if you were to compare this to our very first graphed question, this is a very loose interpretation of it, right? We had exact points on that first one, which is why that first one is a better graph. But this is also okay to get an estimate of what that should be. On the test, you're gonna eliminate the parameter, but you're just gonna give me the equation and you're not gonna graph it. On the homework, all of this is built into one question. It's gonna give you the equations, it's gonna ask you to graph it accurately, and then it's gonna ask you to eliminate the parameter. So part B on each one is gonna be, okay, now find this equation. You can use that equation to verify what your graph looks like, but you don't have to re-graph it. Does that make sense? Okay. So on a quiz or a test, this would be what I was looking for, the equation of the parametric equations with the elimination of the t. Okay, so now we're going to eliminate the parameter. So we want to look at these two equations. Obviously, it gets a little bit trickier with the type of equation. We want to solve one of the equations for one of the variables. So let's say we take the one on the left, and we want to solve for t, not for one of the variables, specifically for t. We would square both sides of this equation. So I get x squared equals 1 squared, which is 1, over the square of the square root of t plus 1, which is t plus 1. Now I want to isolate the t, so I'm going to multiply t plus 1 on both sides of the equation. T plus 1 times x squared equals, these would cancel 1. Distribute here, and I'd get x squared t plus x squared equals 1. Subtract the x squared. And divide by x squared. Then take what t equals and put it in to the other equation in place of that t. So y would equal 1 minus x squared over 1 minus x squared over x squared plus 1. So on this side, you actually have choices. I could multiply the whole thing times x squared, or I can combine the bottom here into 1. So to get that like number would be x squared over x squared. The numerator would be 1 minus x squared over 1 minus x squared plus this x squared all over x squared. These cancel, and I get 1 minus x squared over x squared over 1 over x squared. Keep change, flip here, and I get 1 minus x squared. So that's what y equals. I've eliminated the parameter. This equation, if we rewrite it, can be done with transformations. So x squared means it's a parabola that opens up or down. It's negative, so it can open down. And the plus 1 means it's shifted up 1. So I shift up 1, point my parabola down, and that's the approximation of these, this parametric equations once we eliminate the parameter. So 2 parts of the answer here, the equation itself and then the graph, which again is just an approximation.